Welcome everybody. In this video we're going to give an intro to unit testing for infectious disease models. The example we're using is a cut down version of the example in our paper. If you want the full example or an even larger example, you can go read the paper, the supplementary materials, follow the R markdown from the GitHub repository. We've got a few packages we need to load, and test that is the package we're using, the testing package we're using, and we'll set the seed so that everything we do is reproducible. In this first chunk we're showing the absolute basics of what unit testing is and what it does. So we have a function that we want to test. Here it's the square root function, and we construct our test by writing an expression with some arguments here. We also write what we expect the output from the expression to be here. So if we run this first line, we're saying that we expect the answer for the square root of 4 to be 10. And because that is not what the square root of 4 is, we get this error below that gives a little bit of information about how the result of the expression and our expected output are mismatched. However, if we write up a test properly, we have something like this second line. We're saying that we expect the square root of 4 to be 2, and because those two things are equal and therefore true, we don't get an error nor any output. So depending on what sort of testing framework you're using, you could write a bunch of tests beforehand and run them regularly. If any fail, you get an error that will alert you to the problem. Or if you're using the tests to check a package, then DevTools will return a list of all the tests that failed. So in this example, we're using a very simple epidemiological model. It's an unrealistic model, but great as a learning tool as it's simple. It's a multi-pathogen system with n individuals. Each individual gets infected by a new pathogen every time step and is only infected with one pathogen at a time. Each individual I at time t is defined just by a single letter A, B or C to represent the three pathogens. The entire population at a particular time is defined as a vector, and each time step, every individual's infectious status is updated as a uniform draw from the previous time step's population vector, which is sort of written in here. So one thing we can note from this is that an individual can infect themselves, which doesn't make sense, but that's what the model is. And then an individual that is currently infected with pathogen A might remain infected by A in the next time step. So this image demonstrates the model. This image shows how an individual will move through these states. In a time step, they might leave C and return to C, or they might be infected with C and then become infected with A. So here is our baseline code that performs this model. So we want 12 individuals. We're going to run the simulation for 20 steps. We set up our population matrix with the rows being the number of time steps and the columns being the number of individuals. So that looks like this, a big matrix of NAs. Then we initialize the first iteration of the model. So in this case we want 3 pathogens, and we're just going to repeat this pattern in the first row. So there we go, we've got our initialized population, and then for the remaining time steps we'll loop through, and each time step will draw the new population from the previous iteration's population, sampling with replacement, which looks like that. So each individual is represented as a single column and gets infected with different pathogens through time. This one say. So we can plot what this simulation looks like, and it seems reasonable because it matches our expectation of how that model might behave. However, we argue in the paper that a quick plot is not a sufficient test for correct code. So the first part of writing unit tests for a model like this is to rewrite the code as small functions. It's kind of impossible to just test an unstructured script. It needs to be organized as functions. We've got one function, initialize pop, that initializes the population, builds the matrix and runs the first iteration. And then we've got a second function, update pop, that we iterate over to simulate the rest of the model. The first thing we want to do is just test the very simple cases where we know exactly what the result of a function call should be. So for this initialize population function, we've got 2 tests in this chunk. Our example is very small, just 2 time steps, 3 individuals and 3 pathogens. For the first iteration of that simulation, you can work out beforehand what the result should be. It should be an A and then a B and then a C. So we can run that, and our expectation was correct, and we didn't get an error when we ran that second line. We can go slightly more complicated with 6 individuals, 3 pathogens, and again work out a priori that we'd expect the sequence to repeat twice. And again we didn't get an error, which means our expectation was correct. Similarly, we should test that all the arguments do what we think they do. So we can set a baseline. So if we have a population with 2 time steps and 3 individuals, we would expect that the dimensions of our final population matrix is 2 rows by 3 columns. Yes, that's correct. And now in turn we can alter each parameter and work out what the matrix would look like and see if the output meets our expectation. So if we have 6 time steps instead of 2, we'd expect the second population to have 6 rows, and that is the case. Similarly, if we wanted 20 individuals instead of 3 individuals, then the columns of the final matrix will change. And then in the paper we've got an example for if you change the pathogens argument that's a little bit more involved, so we're going to skip it here. Following on from these easy to set up simple cases, we'll get to the point where we don't exactly know what the result should be, but we can understand the summary of some result. For example, with a bigger population, we wouldn't want to write out everything to say what we think it should look like, but what we can say is that other than the first row, everything in this population matrix should be an NA because we've initialized the population but haven't run any simulations yet. So we can check if that's true, and it is. So that's a slightly more macro or higher level kind of expectation, or a summary of a function output. Similarly, instead of writing exactly what we expect the first row to look like, we can say that the first row should only contain the elements A, B, and C. And that all the elements A, B, and C should be contained in that first row. So that's what the set equal function tests, and again that works very nicely. And then we can run one iteration of the simulation. So now everything except the first 2 rows should be an NA, and nothing in the first 2 rows should be an NA. And yet those expectations are verified. So the next step is to start combining these smaller functions into larger functions that can be run, that can run a typical entire simulation or an entire analysis. So this full sim function initializes the population and then it iterates through the update steps. Again, complexity increases as these functions sizes grow, and it becomes less possible for us to calculate our expectations explicitly beforehand. Instead, we rely more and more on tests based on what the outputs look like. So we can run a pretty small simulation, and after a full simulation we'd expect there to be no NAs left in our population matrix. Here we test that and confirm that it's true. And we can expect that all the elements to be one of A, B, or C. There shouldn't be anything else other than A, B, or C in the output, and again that's true. So we've stitched these functions together and we've tested a more macro level understanding of what we think is happening. One of the difficulties applying unit testing to epidemiological modelling is that a lot of the code is stochastic. So we focus on a couple of strategies for handling this, because Googling unit testing doesn't provide basic tutorials that include stochastic code. It's something that's slightly peculiar to this world of simulations, as most unit testing tutorials are more about software. The first thing is to split up our stochastic code as much as possible to separate deterministic elements from stochastic code. So here's an exaggerated example because this code is only 1 line long. We've got this choose infector function which just picks who infects whom in the next time step and is stochastic. But then these next lines cover the data handling side, where you're taking who infected whom and then finding out what pathogen the infector had and putting that in the correct place in the population matrix. This is deterministic, so we can test this update infectious status function using the previously discussed methods. And doing this split means we can specify our tests to the stochastic or deterministic nature of the simpler functions. We then redefine update pop function to be composed of these two functions. Another way to test stochastic code is by finding parameters for which the stochastic code is no longer stochastic. For example, a Bernoulli trial, if the probability of success is 0, then the answer will always be 0, despite it being a random variable. So the output is no longer stochastic and can be tested with deterministic tests. Similarly, if we put pathogens equals 1 here, then our simulation also becomes deterministic. Because if there's only pathogen A in the population, then in the second time step there can only be A's, as there's nothing else to spread around. So you can set up a population, run the first 2 iterations. We'd expect the 2 iterations to be identical. So we've taken some stochastic code and found a parameter to make it deterministic, but this still isn't testing the core stochastic functionality. So we'll next write tests where, although the code running is stochastic, the test we write is not stochastic. So one way of doing this is with a very small population, or if you know some simple parameter sets, sometimes we can find all the possible outcomes for a simple system, even though we don't know exactly which one the simulation will output. So here we're going to run the stochastic choose infector function with only 2 individuals. So it's different each time. But its result set is very limited. This output 2.1 is saying that individual 1 gets infected by individual 2, and individual 2 gets infected by individual 1. And we can think about this and realize there's only 4 possible outcomes. So we can run this function a lot of times, and then the only possible outcomes are both individuals are infected by individual 1, both individuals are infected by individual 2, individual 1 is infected by individual 2, and individual 2 is infected by individual 1, or individual 1 is infected by individual 1 and individual 2 is infected by individual 2. So while we don't know the result of each individual simulation, we can say something about the range of results that are possible and can then devise a test to confirm that there are no outputs other than one of those 4 options. There's a few more strategies on handling stochastic code in the paper, but now we're going to move on for the sake of time. If other people are going to be using the model, or if it'll be used for different purposes, or you may not return to the code for a long time, then you might want to check the model handles arguments correctly. For example, this here shouldn't be a string but a number or an integer. What we'd hope would happen for this function call is just for it to error. Unlike previously where we compare an expectation with an output for an affirmative validation, instead we just want it to error and say that it's wrong. So we use this expect error function, which if the evaluation of the expression returns an error, then expect error says yes, that was the correct behavior. Conversely, if the evaluation of the expression doesn't cause an error, then the expect error function says, well, that's not what we are expecting. In this line, although it does throw a warning, it does not throw an error because this bit did throw an error, which is what we want. For the final examples, we'll look at some special cases. This is where an argument isn't fundamentally wrong, but it behaves qualitatively differently to the normal way we'd expect the model to behave. So if we're running a full simulation with 2 time steps, 5 individuals and 3 pathogens, this all works fine. However, we might consider what happens if we ask for a simulation with n steps equals 1. This isn't an unreasonable thing to ask for, and we get an error, which is explained in the paper. However, this is a reasonable thing to input, so really we want the code to handle this properly, and so we should just rewrite the full sim function so that we only need to do this loop. We only need to do this loop if n steps is greater than or equal to 2. If n steps is 1, you don't need to run any of this update section, you just initialize the population and return that. So we can redefine our function and then run it without an error and check that the population, we can redefine the function and then run it without an error. and check that the population gives the dimensions we'd expect. So we only wanted one time step, and in the end we've returned the population with only one time step. So thank you very much for watching, and as I've said, if you want to see more details, please go read the paper. If you have any further questions about the paper, please email me or one of the authors. Thank you.